Okay, let's talk a little bit about LeChatelier's principle. LeChatelier's principle states that if you put some sort of stress on a system that's in equilibrium, the system will respond in a way to alleviate that stress. It may shift towards reactants or products, but it may very well shift one way or the other. So, what are some things that would do that? Changes in concentration, that is, if I add a little bit more reactant or product. If I change pressure or volume, if I've got gases in there. Changes in temperature, for example. Now, if I change the concentration, it's going to shift in a way to remove the stress. That is, it's going to shift away from an increase and towards a decrease. That is, if I have some way to remove a reactant or product, it'll shift towards the decrease. If I add a reactant or product, it's going to shift away from the increase. So if we look at H2 plus I2 going to form 2HI at 450 degrees Celsius. If we remove some H2 from that reaction, then the reactant will shift towards reactants. If we add some H2, the reaction would shift towards products. Changes in volume and or pressure. Changing the volume in a gas phase reaction will alter the pressure because of our ideal gas equation, PV equals nRT, if all other factors stay equal. The reduction in volume increases the pressure, and it will increase if the volume increases, then the pressure will reduce. And so the shift will happen in a way that will alleviate that. And so what you have to do is look at the number of moles on the reactant and the product side. The side of the reaction with the fewer moles, it'll shift that way if the volume is reduced, and towards a greater number of moles if the volume is increased. If the number of moles is equal in reactant and product size, changing the volume will not affect the position of the equilibrium. If we consider N2 or NO2, 2NO2 is going to N2O4, where Kc is concentration N2O4 over concentration NO2 squared. If the volume increases, then the equilibrium will shift towards the side with the more moles. That in this case is the reactant side, because there are more moles of NO2 at equilibrium. So Q is bigger than K in that case. If the volume is decreasing, the equilibrium will shift towards the side with fewer moles, the N2O4 side, or the products, towards the formation of N2O4, because Q is less than K. If you change the temperature, it depends on whether it's endothermic or exothermic. Here's NO2 in equilibrium with N2O4. NO2 is that reddish color you see. N2O4 is colorless. So at cooler temperatures, we can see that red color is lighter. And at higher temperatures, when it's not, at least in room temperature water, if not warm water or hot water, then the red color is much more significant, indicating a shift towards the NO2. So it seems like reactants are favored in warm or hot conditions, where the N2O4 is favored in cooler conditions. So if the reaction is exothermic, then heating the reaction will produce more products, or endothermic, the heating reaction will produce more products. If it's exothermic, then it will produce more reactants. And so in this case, heating it produced more reactants. So we would conclude that this reaction is at least modestly exothermic. Think of it as writing heat as a reactant or product, and treat it the same way the concentration would be. So cooling it off would be removing heat. Heating it up would be adding heat. And if you write heat as a reactant or product, you can treat it in the same way you did the concentration. And so we would say two NO2s is in equilibrium with N2O4 plus heat, indicating that reaction is exothermic. Action of catalyst wasn't in the initial list because catalysts do not affect the position of equilibrium. It will allow it to reach equilibrium more quickly if it's an equilibrium reaction, but adding a catalyst does not affect the position, so it won't shift with the addition of a catalyst. And so we can see the catalyzed versus the uncatalyzed again. We can see the activation energy of the catalyzed reaction is lower and there's 2 humps instead of 1, indicating a likely intermediate. But that won't affect the position of the equilibrium because the energy and the reactants and the products are the same, and therefore the position of the equilibrium is unaltered, so that won't produce any sort of shift. And so if we look at for instance, example 15.8, we got 4 ammonia reacting with 5 oxygens plus heat is in equilibrium with 4 NOs and 6 H2Os in the gas phase. So disturbing the equilibrium in the following ways: does it favor reactants, products, or would it have no effect? So if I decrease the temperature, it would be like removing that heat on the reactant side, that heat right there on the reactant side. And so it would shift towards reactants. If I add some ammonia, ammonia again is a reactant, and so it's going to shift towards products. It's going to shift away from an increase and towards a decrease. If I remove some O2, that's a reactant, so it's going to shift towards reactants. If I add some NO, it's going to shift again towards reactants because NO is a product. If I add a catalyst, no effect. Now, there's a problem after this. That's a study question, and I want you to practice that one and see if you can do what we just did. Here is another example which I'll work through. And this is related to gas phase reactions and increasing or decreasing the volume. In fact, each of these reactions. So if H2 plus I2 goes to form HI, if I increase the pressure by reducing the volume, since the moles of gas are the same, then it has no effect on the equilibrium. And so A would be no effect. We have the reaction we just had going in the previous instance. 4NH3 plus 5O2 goes to 4NO and 6H2O, all in the gas phase. We got 10 moles of gaseous product, but only 9 moles of gaseous reactants. And so increasing the pressure by decreasing the volume is going to favor a way that will relieve that excess pressure, so it'll shift towards the side with fewer moles of gas, in our case, the reactant side. PCl3 plus Cl2 goes to PCl5. There are fewer number of moles on the product side in C, so it's going to shift towards those fewer number of moles, or the product side. 2H2 plus O2 going to 2H2O in the gas phase. Looks like there are fewer moles of gas on the product side, so it's going to shift towards products. And so that was a brief description of LeChatelier's principle and how things will shift.